Fractals are sometimes called the pictures of nature, and if chaos theory, as the name implies, is the chaotic and unpredictable dimension to nonlinear systems, then we might say fractals represent their orderly side. We see lots of order in our world. The Earth goes round the Sun today, and it will do the same tomorrow and the next day for millions of years. If we take a butterfly, we see that one side of it is almost exactly mirrored in the other. We see the same in the regular geometric forms of snowflakes. One way of understanding this order is through the concept of symmetry. In mathematics, symmetry can be defined as an object or process that is invariant to a transformation. In more familiar terms, this means something that stays the same despite a change. So with our example of the butterfly, its external physiology had a reflection symmetry, meaning we can simply flip one side over and we'll get the other side. The same was true of our snowflake, and we can imagine some symmetry in the pattern of Earth's orbit. Without these symmetries to our world, the scientific endeavor would be very difficult, because science is about the creation of compact representations of the world. It is like we're creating a map of the world, and it is only through finding these symmetries and encoding them in models that we can describe a wide variety of phenomena with simple equations. Without these symmetries, our scientific map of the world would have to be the same size as the world itself, and thus useless. Symmetry and its counterpart asymmetry are then two of the most powerful concepts in mathematics and science for talking about order and chaos. They help us to understand these abstract concepts in a distinctly geometric and visual form. So with the phenomena of chaos, we saw this breaking of symmetry, as two things that started out similar became increasingly dissimilar as the symmetry between them became broken, and the result was, after a short period of time, complete asymmetry. Fractals have what is called scale invariance. That is, they have a symmetry with respect to scale, meaning the scale can change, but the structure will repeat itself over various levels of magnitude. This scale invariance is also called self-similarity, and it is this type of symmetry under magnification that defines fractals and gives them an amazing type of structure and order. Fractals are both mathematical constructs that derive out of iterative functions and real-world phenomena. In this module, we will present them as mathematical models, and then in the next, look at their real-world counterparts. As we've seen with most of nonlinear systems, the core ideas behind fractals is a feedback and iteration. The creation of most fractals involves applying some simple rule to a set of geometric forms or numbers, and then repeating the process on the result. For example, the most famous fractal, called the Mandelbrot set, so named after the discoverer of the concept of fractals, is a product of a simple iterative function on complex numbers. We'll not go into the details of complex numbers, but the iterative map itself is quite simple. There are many extraordinary things about fractals, but the first thing we'll note is the infinite variety that these simple iterative functions can produce. Whereas most Euclidean shapes, what we might call normal shapes, tend towards a bland featurelessness as we scale them up. If we take something like a circle, the more we zoom in on it, the more it will start to appear like a bland straight line. And this would also be the case for other regular shapes such as squares, triangles, and so on. The iterative functions behind fractals, in contrast, give us an infinite amount of detail and structure within their form. Irrespective of if we divide the shape into two or divide it into a million, each of these million little parts will itself have an infinite amount of detail and a form that resembles the whole. Just as there can exist an infinite amount of form in a finite object, there can, in fractals, also exist an infinite length within a finite length. This is best demonstrated by a fractal called the Koch curve, that can be obtained by iterating a simple process of dividing a line and placing a triangle in its center, and then iterating on this to divide the line on the triangle in a similar fashion. What we get when we do this is a path that will in fact have infinite length to it. If we were to try and trace a path along this line, its infinite detail would prevent us from ever reaching the end. Thus this finite length contains an infinite length within it. The last thing we'll note about fractals is their scale-free property, meaning that no scale is the proper frame of reference. Most linear systems that represent regular forms have features and structures within a limited range of scales. Thus, if we plot these features, we would get a normal distribution, with the majority of features tending towards some kind of mean, giving it some kind of normal frame of reference with respect to scale. These nonlinear fractals, as we've noted, have scale invariance, meaning we find features on all levels, resulting in there being no normal distribution to their occurrence, and thus no normal frame of reference. The occurrence of features is instead distributed out in a power law. Big features exist but are very rare, whilst many small features also exist, and this long tail does not drop off because it is a fractal, it goes on infinitely. Thus we can say the power laws we encountered in an earlier module are the algebraic expression of the scale-free structure to fractals. And just as there is no normal scale in fractals, there is no normal average to power law distributions. In this section, we've begun our exploration into the amazing world of fractals that has once again exhibited the extraordinary results we can get from simple nonlinear feedback loops, this time in their capacity to produce structures that have a scale invariant property, giving them the very counterintuitive capacity to contain an infinite level of variety and length within a finite form. In the next section, we will continue our discussion on fractals by looking at some real-world examples in pictures.
Patterns of life. Number 5, chaos theory. Why can't we get a good weather forecast? And just what are the chances of sudden apocalypse? Chaos theory is the noble attempt to solve such quandaries by studying chaotic systems. These are systems where even a slight change to the input can cause a huge, unpredictable outcome. They led meteorologist and bank holiday ruiner Edward Lorenz to declare long-term weather forecasting utterly impossible. In chaotic systems, any inaccuracy in your starting values quickly multiplies and leads to a different result, turning a seemingly benign trip to Torquay into a dangerous game of Russian roulette. It's not just your holidays chaos curtails. The orbits of Mercury, Venus and Earth all affect each other in a chaotic systems kind of way. Mathematical models show a 1% chance that at some point in the next 5 billion years, Mercury could crash into either Venus or the Sun. And chaotic systems are everywhere, ruining our best laid plans and turning weather forecasting into the twisted ramblings of a fantasist.
How fast does a colony of rabbits grow, assuming that, well, they breed like rabbits? If mature rabbits produce a new litter every month, at first you'll have just the one pair, then 2, then 3, and then 5 pair as the offspring start having litters of their own. Soon the colony is growing fast, 8, 13, 21, 34, and then 55 pairs of rabbits. These are the numbers of the Fibonacci sequence, named after 13th century Italian mathematician Leonardo of Pisa, better known as Fibonacci. He introduced the rabbit problem about 800 years ago. The sum of 2 consecutive numbers in the Fibonacci sequence gives you the next number. Of course, real rabbits don't breed so predictably, but surprisingly, the Fibonacci sequence is common in nature. Look at the head of a sunflower. It typically contains 2 types of spirals, 34 spirals in one direction and 55 in the other. 34 and 55 appear back-to-back in the Fibonacci sequence. Some sunflowers have even larger Fibonacci numbers, such as 89 and 144. Pine cones often display similar patterns with 8 and 13 spirals. Again, consecutive Fibonacci numbers. This can't be coincidence, and in fact, there's more math at play. For a growing sunflower, it's beneficial to push out each new floret as far as possible from the existing florets. That gives each floret the most space to grow. Studies have shown that under many growth conditions, each floret should emerge at an angle of 137.5 degrees from the one that came before. Amazingly, 137.5 degrees is a well-known angle called the golden angle. It's famous for being derived from a number called the golden ratio, or phi. The golden ratio is closely related to the Fibonacci sequence. Take any number in the sequence, divide it by the one that came before, and voila, a good approximation of the golden ratio. So the golden angle produces the most efficient use of the sunflower's limited space. And the relationship between the golden angle, the golden ratio, and the Fibonacci sequence is what causes the sunflower spirals to appear in numbers straight out of Fibonacci. As beautiful as the sunflower is, isn't it even lovelier knowing that there's a deep mathematical order to it? For Scientific American's Instant Egghead, I'm John Matson.
We learn about calculus in high school, and we know it includes integration and differentiation. But what is it actually used for and how? The language of calculus appears everywhere in modern science and technology, whether we're modelling the rise and the fall of the stock market or determining exactly when a space rocket will arrive into Earth's orbit. It's the language invented for the specific purpose of describing the dynamic nature of our universe. To put it simply, calculus is the maths of motion and change. The word calculus originates from the Latin word meaning pebble. The Romans used pebbles to perform calculations on an abacus, and the word became associated generally with computation, just like the word calculator. The beauty of calculus is not just in the maths alone. It's in the way that calculus can form a connection, a relationship, and a language to describe the dynamic nature of our world. There are unlimited uses and benefits of calculus in any field. Calculus is the language of motion and change, and by using calculus, we have the ability to find the effects of changing conditions on a system like the weather, for example. In the atmosphere, we have changing temperature and changing pressure. So by using differential equations, meteorologists can indicate and predict the weather for our benefit. Calculus holds incredible power over the physical world by modelling and controlling systems. It's the language of medical experts, scientists, engineers, statisticians, physicists, and economists. If a quantity or a system is changing, we can use the mathematical modelling of calculus to analyse the system, find an optimal solution, and predict the future. Motion, electricity, heat and light, harmonics and acoustics, astronomy, radioactive decay, reaction rates, birth and death rates, costs and revenue, all of these can be modelled beautifully using calculus.
What is math? Some people seem to think that math is some ethereal set of unrelated rules and symbols. In this video, I will explain how the rules of mathematics follow logically from one another, how a new mathematical concept is really just built off of previous foundations. Math is really a set of rules that follows from a simple set of axioms, or a statement that we regard as true, with which we can build the rest of our rules. To start off, we define our basic unit of mathematics as the number 1. Next, we define our first operation, addition. We can define all whole numbers in this way, and from addition we can get all of our digits. 1 plus 1 equals 2, 2 plus 1 equals 3, 3 plus 1 equals 4, and so on until we get to 10. In our number system, the numbers start to repeat after 10. We call this base 10. It doesn't have to be this way, but it's another axiom we use to build our system. To review, so far our entire mathematical system consists of whole numbers that we have found only using addition and the number 1. Next, we define subtraction as the opposite of addition. No new rules are introduced, only the inverse of addition. Now let's build our next mathematical operator, multiplication, from what we already have. We can define 2 times 3 as 0 plus 2 plus 2 plus 2. Any multiplication with whole numbers can be found this way. 98 times 86 is 0 plus 98 plus 98 plus 98 until there are 86 98s. We can build division off of multiplication by defining it as how many times you must multiply a number to equal another number. Notice that there are still no more new rules. Division is based solely on multiplication, which we built off of addition. So to divide 56 by 7, we do 0 plus 7 plus 7 plus 7, and count the 7s until we get 56. In this case, there are 8 7s. Now through the axioms of the number 1, addition, and a predetermined base 10 system, we have created subtraction, multiplication, and division. You can continue to extrapolate these ideas to reach exponentiation, square roots, and all other sorts of mathematical wonders. Advanced mathematical concepts weren't pulled out of thin air, they were built upon previous stepping stones.
Sometimes simple questions are the most complex, such as, what is math? Math is the abstract study of how the structures of systems relate and operate. Or, more romantically, math is often referred to as the language in which the universe is written. Now, like our universe, there are parts we understand well, and parts we still know nothing about. But when your teacher gives you a math problem, he or she is giving you a problem that people already know how to solve. To get a better understanding, let's take a big step back and look at a simple caveman example. And let's say this society has no concept of numbers, but they recognize there can be multiples of things. In math terms, this could be explained as 0, 1, and many. Depending on how such a society is structured, this might work just fine. But what if one day you find a hole near your garden of many carrots? You think a carrot might have been there, but since you still have many, you can't be sure of this. You might decide it's a good idea to find a better way to keep track of your carrots beyond just many. Your first idea might be to draw a line right by each carrot. That way, if you come across a line with no carrot next to it, then you can be certain that there's a missing carrot. But what if someone steals a carrot and erases the line at the same time? To handle this, you might keep a record of these lines inside your cave or hut. But to do this, you need to give names to specific quantities of lines. So you start developing numbers. Now you have a concept of 20 being different from 19. This way, you can count lines, then go out and count carrots, and see if they match. Sure, your system of one line for one item gets tricky when dealing with really large numbers, but since you rarely have to deal with hundreds of thousands of anything, that's more of a problem for later civilizations like us. But what we see here is that math is a method of modeling reality, but yet it departs from reality in just the simplest of calculations. 1 plus 1 equals 2, for example. There is no such thing as 2 in nature. There is just a carrot and another carrot. But because they both exist, we can group them and call it 2. And if we have another instance of that, we would have a carrot, another, and another. Now, math can't exist without human thought, but what it models persists throughout nature. Not every aspect of math is guaranteed to have a real-world equivalent, but it's specifically designed to be identical to reality. Finally, it should be noted that since mathematics is an abstraction, there will be cases where things will work in the abstract, but will make no sense when you try to apply it back to the real world. For example, any child could easily think of a number so large that it's more than all the individual measurable objects in the universe. Now, that number exists and is perfectly sensible in the abstract realm of mathematics, but it still has no meaning or use in the real world.